In this video, we're going to be talking about how to find the intersection between two graphical functions. So you looked at grade 9 how to find the intersection graphically between two lines, and in fact you also explored how to look at it algebraically with substitution and elimination. Our focus is going to be on scenarios like these, where we have a parabola or a quadratic that's crossing with lines or potentially intersecting lines in some way. And so there's a few different scenarios that can occur when it comes to a line interacting with a quadratic or a parabola. And so we're going to look at all three of those here, and I've color coded them so we can go through them in order. The first one we're going to focus on is the blue line. So if you're looking here at this diagram, the blue line crosses a parabola in two different spots. So we would actually describe that line as cutting the parabola. So it has 2 points of intersection. The red line is only intersecting the quadratic in a single spot, the point that I've labeled there. And we would describe that line as being tangent to the parabola. And then the yellow line finally doesn't intersect the parabola at all. In fact, if you extended both infinitely, they would never cross. And so the yellow line is the type of line that will never intersect with the parabola. Now the placement of those lines is not specific. The blue line could move up or down, and it would still cross the parabola in two different spots, and the yellow line could move up or down, as long as it doesn't pass the red, and it would still miss the parabola entirely. And so you have to keep in mind there's a whole family of lines that cut the quadratic and a whole family of lines that miss the quadratic. The tangent line that I have there, though, is sort of in one particular spot. So there's a few different scenarios that can happen with a line interacting with a quadratic. But I want to look at how we actually find those points of intersections. And I want us to focus on doing that algebraically right now, and we'll look at graphically a little bit later. So when it comes to finding a point of intersection algebraically, we have to remember that a lot of the skills we learned with lines intersecting each other are still applicable here. So I'm going to look for the points of intersection between the quadratic x squared plus 8x plus 15 and the line given by 4x plus 12. So I have these two separate equations. I want to figure out where they cross. I want to find those points of intersection. And the key is, where they intersect, the x and y values of the points will be the same. So what that means is I can take these two equations for two different graphs and I can set them equal to each other. So they're both equal to y. I want that y value to be the same, so I set them equal. So I now have x squared plus 8x plus 15 equals 4x plus 12. And I can gather like terms to one side and get this to be a very simple quadratic equation to solve. X squared plus 4x plus 3 equals 0. I just have to factor now to get my values for x. So I get x plus 3 times x plus 1 is equal to 0, which tells me that x is equal to minus 3, or it's equal to minus 1. Now I'm not done yet, because I'm looking for a point of intersection, and just having the x value isn't going to cut it. And so what I need to do then is take these x values, and I'm going to plug them back into one of my equations. Now I'm choosing the line, because typically the line is going to result in you having to do less computational work in your head. So when you're doing it at x equals negative 3, we plug that back into the line, evaluate it, we get a y value of 0. So that's my first point of intersection between the quadratic and the line. It's at negative 3, 0. At x equals negative 1, I take that and pop it back into the equation for a line. And so when I evaluate that, I'm going to have 4 times negative 1 plus 12. Now that's equal to 8. So that's the y value of my other point of intersection. So I've got one point of intersection that's negative 3, 0, and another one that's negative 1, 8. So those are my 2 points of intersection, and that's basically how you'll find the intersection in any scenario. Now here I step up the difficulty a bit, because in this example I want to look at the missing parameters again. So for what values of k does y equals kx plus 1 cut the parabola given by y equals x squared plus 2x plus 5 over 4? Now I know that this might look fairly intimidating, but you actually have all the skills at this point to solve this type of problem. So we're going to start the same way we were looking for the points of intersection in the last example where everything was numerical. I'm going to set the equation for the parabola and the equation for the line equal to one another. Now my next step was to move everything to one side and gather like terms. That's a little bit more awkward in this case because I have to do this algebraically. So notice as I move everything over, my coefficient on x is 2 minus k. I can't gather those like terms perfectly, so that's how I have to express it. So I now have this quadratic equation, and it looks absolutely terrifying to solve. And in fact, I can't solve it because the parameter is still missing. So I'm not actually going to find the solutions just yet. In fact, I'm not actually going to find the solutions, the points of intersection at all. I'm still trying to solve for a value of k that guarantees that the line cuts the parabola. And that's the key word. If it cuts the parabola, that tells me that it looks something like this, which tells me that there are 2 points of intersection, or 2 solutions to this quadratic equation. And as you're going through this, you should be thinking, what does that mean? Well, 2 solutions, that means the discriminant of that equation has to be positive. And so we're making these logical steps to figure out what to do next, and it leads us to the discriminant. So we know the discriminant's equal to b squared minus 4ac. If I plug in my parameters here, you can see I'll work out the algebra. I have 2 minus k squared minus 4 times 1 times a quarter. And so if I expand that out and start to gather like terms, I end up with 4 minus 4k plus k squared. And from that second part of the discriminant, it works out to just be a minus 1. And so when I simplify this, it actually works out to be quite a nice quadratic of k squared minus 4k plus 3. So the question is, when is that positive? That discriminant is on its own a quadratic. So I need to figure out when that is a positive value and when it's not. I'm going to start by actually figuring out when it's 0, because that's going to help me set up my sign diagram. So I'll set up this quadratic equation, k squared minus 4k plus 3 equals 0. I factor it. I get k minus 3 times k minus 1, which tells me that k is equal to 3, or k is equal to 1, when the discriminant's equal to 0. So that lets me set up my sign diagram to start. I put those lines on as sort of the barrier lines of 1 and 3. That's when the discriminant's equal to 0. And now I need to check other values of k to see in those intervals whether the discriminant's positive or negative. So I'm going to look in the interval where k is less than 1. And the value I'm going to substitute in is k is equal to 0. I pop that into the discriminant, and I realize I get a positive value. So for any k less than 1, the discriminant is positive. Next, I'm going to move on to the next interval between 1 and 3. So these are all the k values between 1 and 3. I'll pick 2 and sub it into my discriminant, and I get a negative discriminant value. Then I'll move to the last interval where k is greater than 3. I pick a test value of 4 just to sub in. I get a positive discriminant in that instance. So what I've done here is I've just evaluated those values of k in the discriminant and discovered the 2 regions where it's positive are the ones that I've circled here. And so to write out my answer, I will say that the line cuts the parabola specifically for those 2 instances. So the 2 intervals are when we have k greater than 3, that's the interval on the right, or k less than 1, that's the interval I have written on the left. So those are the values of k, or the ranges of k, that result in the line cutting the parabola. And so you could also tell me what values of k will make the line tangent. If k is equal to 1 or k is equal to 3, the line's actually going to be tangent to the parabola. And if I pick any value for k that's between 1 and 3, the discriminant is negative, meaning that the line is not going to touch the parabola at all. And so by doing this test, I'm actually able to figure out what parameter I can put in for the line that's going to make it meet these different criteria. So I figured out the ranges of k where the line will cut the parabola, the values of k where it will be tangent to the parabola, and the range of k values where it's not going to touch the parabola at all. And so this is an application of the discriminant to looking at intersections of functions. And so some of the questions you'll be solving today will look like this. They'll be solving for a missing parameter. Other ones you'll just be solving for the points of intersection. But it's important to remember the methodology is the same. Set the equations equal, solve, or if there's a missing parameter, use the discriminant to find the missing value. So that's the end for this video lesson. I know it went by pretty quickly, but it's basically meant to be a primer for this topic. There's lots of great examples in the textbook as well that you can work through. Really what I want to make sure everyone's doing is practicing using the discriminant to solve problems. So work through the exercises that are listed on your unit outline. That's going to give you a sense of which questions are the best practice for developing this particular skill. And then we will talk about this tomorrow when I return.